Today, I'm going to talk about self-healing materials inspired by bone. And the first thing I want to do is just talk about what bone is made up of. So as engineers, we can think of bone as a polymer ceramic composite, whereas biologists might describe it as like crystalline collagen fibers plus a crystalline hydroxyapatite mineral. So what does that actually look like physically? So we have our collagen, which is a protein. And so it is just a series of amino acids connected by peptide bonds. And that then can be structurally arranged more with intermolecular hydrogen bonds to give it more structure. And then the secondary structure of an individual collagen molecule can come together and form a structure where you get three collagen molecules that are connected by intramolecular hydrogen bonds to give this tropocollagen structure. And this tropocollagen is actually the basis of what makes up bone. And then you have the hydroxyapatite mineral, which I'll just write as HAP. And that is a calcium phosphate based material. So generally looks like this. And so these two things come together to form bone. And the way that that looks is something like this. So you have these tropocollagens that begin to align in whatever direction the bone layer is trying to align in. And they end up forming kind of these periodic gaps. And those periodic gaps are really ideal for the nucleation of the mineral to occur. And so nucleation is really just the starting formation of the mineral. And then from there, it grows up and up and up into a crystal. And nucleation of minerals requires a certain activation energy barrier to be overcome in order to start getting that crystal. And the rate at which that nucleation starts to occur is defined as J equals N star times beta. So this is rate of nucleation. And you have N star is the number of active nucleation sites. And a nucleation site is just somewhere where the mineral will start to form. And so that is really dictated by surface organization. And for us in bone, the periodic nature of the tropocollagen alignment means that these gaps in between molecules are the perfect nucleation sites for that hydroxyapatite to start forming. And so the structural organization of the biopolymer controls the mineral nucleation in that way. And then this beta term is the diffusion of the mineral molecules to the nucleation site. And that depends, on a lot of things, temperature and pH, but specifically it depends on the saturation of the solution. That is really critical. And the saturation is how much of the mineral molecules that you have available. And so for this hydroxyapatite, as you see up here, we need the calcium, the phosphate, and hydroxide groups. A key term for saturation is the solubility constant. And the solubility constant describes the value at which that nucleation will occur. And it depends on the concentration of your different components and their activity coefficients. So that describes how the nucleation will occur. And as I mentioned, it's going to end up having those hydroxyapatite crystals in between or intercalated between the tropocollagen molecules. And just to reiterate, supersaturated solutions and highly organized surfaces decrease the activation energy barrier, and that's what allows that mineralization to occur. And this is not just for like the initial formation of bone, but this is the same method that's used in self-healing. So if you break your bone, your osteoblasts start to lay down new bone, and this is what the actual chemical molecular structure is going to look like when they do that. And self-healing is a trait of biological materials only. And so scientists have been trying to replicate this for a while. And the general scheme that's used for self-healing is to take one material in a liquid form and another material also in a liquid form, that when those two liquids come together, they end up forming a solid or polymerizing. And if you imagine that being embedded in a matrix material, so you have different liquids, when a crack starts to propagate, if you have liquid A and liquid B being cracked open, then they're going to start to flow into this space and they'll start to polymerize in that crack. And that's how you can start to get healing that doesn't require intervention from the scientist. It's just it's self-sensing. So its release is driven by the actual formation of the crack. And one of the applications where self-healing would be interesting is in construction materials. And so the application I looked at was self-healing concrete. And normal concrete actually has some slight ability to self-heal on its own anyway. It's called autogenous self-healing. And it's basically just when unreacted cement particles are hydrated, it just ends up forming that same cement paste that was there in the first place. And it can seal cracks up to 300 micrometers. But we can improve that with different other strategies. And so we want to use autonomous self-healing, which is just using chemical or biological reagents embedded within the material that are released when the cracking occurs. And so the specific reagent that you use, there's a bunch of different examples in the literature. One of the ones I thought was most interesting was actually bacteria that can produce different materials to fill the crack. But what I focused on was a hydroxyapatite application, just because, I was really interested in the bone piece. Hydroxyapatite, as we've talked about so far, is a calcium phosphate composite or calcium phosphate mineral. And this generalized form here is the stoichiometric form. Bone is actually non-stoichiometric. And so it doesn't look exactly like that formula. You can get CDHA, which is calcium deficient hydroxyapatite. So that just means that you have a reduced calcium to phosphate ratio. And then you can also get CCDHA, which is carbonated calcium deficient hydroxyapatite. So again, we're decreasing that ratio, but we're also replacing certain groups with carbonate. And so there are actually two types of this. You have type A, which replaces, replaces one of the hydroxide groups, and type B, you have it replacing phosphate. And so this first type A actually occurs more so in high temperature situations. So if you have our usual hydroxyapatite plus CO2 as a gas in high temperatures, you end up forming the CCDHA plus water. So that actually ends up looking like this with the carbonate molecule. And again, because it's calcium deficient, you probably actually wouldn't have this as 10. It would also be reduced compared to the amount of phosphate you have. But the key piece is where this carbonate is being replaced. And most of the time you actually end up with type B rather than that type A because it requires that high temperature. And so what the researchers did for their self-healing concrete was to actually, they were actually trying to create these CCDHA and CDHA molecules as their healing paste between the concrete. And so if you imagine a little slab of concrete with a crack in it, right? You have your concrete or cement, which contains calcium carbonate. So there's your source of calcium ions. And they put within that this hydrogel that contained phosphate. So hydrogel with phosphate, HP. And when the crack starts to form and it hits one of these HP spots, the hydrogel will begin to release phosphate out. And so in this crack, you end up getting a population of phosphate molecules. You have calcium available. And then from the environment, you can have water coming in and you can have carbon dioxide coming in. So together, those will end up forming the carbonate and the hydroxyl groups. And so you end up getting all of the different components that you need for that self-healing to start to occur. So if you ended up having calcium plus the hydroxyl plus or hydroxide, and then the phosphate, then you'll probably end up with CDHA, so calcium deficient HA. And again, that's just due to the amount of calcium that's available versus the amount of phosphate that's available. But if you end up substituting the or some of the phosphate for the carbonate, and they were able to form CCDHA. And together, those two forms of hydroxyapatite filled the crack and they were able to get 95% healing. But I also wanted to use this as kind of a lesson in reading papers carefully. So they were able to get 95% healing, which is more than traditional concrete does. However, the compressive strength, so that's what they were measuring healing by, is the change in compressive strength. The compressive strength of the cement that's impregnated with this hydrogel was actually just significantly lower than traditional concrete. So while they were getting 95% healing, the healed concrete was still not as strong as the concrete would have been to start with if they hadn't put the hydrogel with phosphate in there. So I do think this has a lot of potential. I just don't think that this paper necessarily was being as honest as they could have been. I also think that this technique could be really improved if they were able to also have a polymer involved to control the nucleation. And I've learned a lot about toughening mechanisms of bone, which actually just prevent crack propagation in the first place, which is a great question to ask me about in the comments, whoever watches this first. And I think that could also be an avenue to pursue that would just reduce the need for self-healing to start with.